And welcome. Today we're going to be talking about surface area. So what we have here is what we've been doing so far has been double integration. Of the form integrating over some two-dimensional region D with f of x comma y, dA, and the basic story here is we have some region, we'll call that D, and there's some sort of function that sits over the top of it that this is our function f of x comma y, and that defines some sort of surface, if you will, that's embedded in three-dimensional space. And so, of course, there's a lot of surfaces out there, and only some of them can be defined as functions. Other surfaces aren't one-to-one with the xy plane that sits within the space. But the idea is that all surfaces are fundamentally two-dimensional objects. So but what we're doing here, what this integral is, right here, we think of this integral as kind of a volume, right? Because what we're doing is we're taking some tiny patch, call that delta A. We're projecting that up. We're finding some representative value of f that lives on that patch. And that creates a height to a little rectangular column. And that column, if I can now just kind of excise that out of there, looks like that. And that column has some little volume I, and the idea is that the integral, this capital volume, is just going to be the sum of all the volumes created by all these little rectangular columns. And that's essentially the idea behind double integration. Now, obviously there are details of, well, if f goes below the xy plane, then the volumes that we're computing are negative volumes, but the idea is fairly straightforward even then. And so now a surface area is a totally different thing. So what we want to do now is actually talk about some surface, and we're going to consider surfaces only in, so we think of a little patch there as being delta S. And this surface will live inside of we're embedding our surface always in three-dimensional space. Like that. Okay. So this surface then, but it's still a fundamentally two-dimensional object. And what we like to do is think of each point. So I'm going to make a little point right there. I'm going to call that point x0, y0, z0. That's a point that's in three dimensions, but it's a point on the surface. So we want to come up with a function, right? So these surfaces are fundamentally two-dimensional objects, and so we should be able to create a mapping, a vector function of the surface. So this is how we do it generally. So we want this vector function I'm going to call R the vector, and it's going to be a function of two variables, two dimensions, and we'll call them u and v, right? So they're not going to be the xy. It's not going to be those two dimensions. It's going to be some other abstract two dimensions here, u and v, and it's going to be, and we write it like this: I is our unit vector times x uv plus j, the y unit vector times y u comma v plus k, the z unit vector times z u comma v. All right, so again, these things are functions. They're going to be what we'll call 2D input functions. and that's going to create our x, y, z. So we can think of this as literally producing a vector x, y of z that's going to be a function of these two inputs. And so the idea here is that we have some other domain. Think of that as our, sorry, I'm going to redraw this. I think of it as a domain like this, u, v, and it lives in a separate world from the x, y, and z coordinates. And there's some domain in there, call it d. And this is again a two-dimensional. This is a two-dimensional space, and we're going to create a mapping, and that mapping, that function, that vector function r, that's going to map u and v into our three-dimensional space. So the question then is, how do we use this idea to find out something about this surface? Most importantly, its surface area. So we're going to think of there's a patch in D, and there's a point in it of U0 and V0, and that's the point that gets mapped to our point x0, y0, z0. Okay? And that point's there. And now if I move up this way, say, by some, I'm going to call that delta V, that's going to move forward that direction. And if I move in this direction, I'm going to call that delta U. It's going to move our point going in that direction. So we think of these as two vectors. I'm going to call this vector P and that vector Q. And they're the vectors, so P, the vector, it's going to emanate from x0, y0, z0, which is going to be equal to what I'll call r0, right? And that's going to be this point defined by evaluating at u0, v0. And then it's going to r u0 plus delta u times v0. Okay, and our q vector is going to be from, again, our r0 point, right? And it's right here, and it's going to be going in that direction, and it's going to be going to r at u0 comma v0 plus delta v. All right, so that's good. So now I'm going to blow up our little picture there. So there's our p vector, and starting at what I'll call the x0 vector, or our r0 vector actually, I'll call it r0, and it's going to what I'll call r delta. Oh, sorry, I'm mislabeling this. This one is the q vector. We have another one in this direction. I'm going to draw it like this a little bit. This is our p. So this is going to be the delta v vector, and this is going to be r, the vector, delta v, or sorry, delta u, right? So there's our p and our q. All right, so the question is then, these create the side, two of the sides to this area, which we'll call delta s. So the question is, how do we find that area? So the area so delta s, the area of surface patch we're going to be able to get it by, so any two vectors, if we think of the patch that's formed by P and Q, so P and Q form a parallelogram. And then the area of that, so So delta S is going to be the magnitude, the vector magnitude of P cross Q. Alright, so that's good. So what is P cross Q? Well, let's study a little bit more about what P is. So I said P was from R0, our point right there, to this point that is achieved by moving U from U0 to U plus delta U0 plus delta U. Okay, so that creates this direction here. The same thing going for the V direction. We go that way by causing V0 to move to V0 plus delta V. All right, so that creates this little parallelogram. So we want to be able to actually calculate the exact value. So, and we want to do this. So for smaller and smaller delta V's and delta U's. So the idea here is that R is going to be equal to, and this is going to be approximate, R0 plus what I'm going to call the partial derivatives. So I'm going to say that this is going to be it's going to be partial x with respect to u plus j, the vector j, delta y, delta u, plus k. So I'm going to call this, so this is always an approximation I can do for any perturbation like this, delta u, right? And that's the k vector, and that's going to be delta z, partial z, partial u. Right, and we're going to evaluate this whole thing at u0, v0. Okay, and then what we're going to do then, to make this an approximation, we're going to do a linear approximation. We're going to multiply it by delta u. All right. So it turns out then, of course, I said that P was the vector from R0 to this vector that's perturbed a bit, and of course all we have to do then is then P is going to be the difference between the two. It's going to be R delta U minus R0, which of course is exactly this thing right there. And Q is going to be very similar. It's going to be I delta x, or partial x, partial v now, plus j, partial y, partial v, plus k, partial z, partial u, partial v, and we're going to evaluate that also at u0, v0. And then we're going to, because we're doing a linear approximation, we times it by that small perturbation, delta v. Okay, so there we go. So that's our u and our v. And so these vectors right here, they actually have, in the textbook, they call this vector rv, and this vector here, they call this ru. All right, so there we go. So we can rewrite our delta S now as ru times, right here there's a delta u, so we times it by delta u, and we do a cross product times rv. So this is the partial of r with respect to v and all of its components right there, and then we're going to multiply that by delta v. And then we're going to take the length of that resulting vector from the cross product, and this becomes, so because scalars can always move outside of any kind of norm, vector norm, or also the cross product, what we end up getting is delta S is equal to RU, the partial of R with respect to U, cross the partial of R with respect to V, times delta U, delta V. All right, so what this represents then is that if I want to find the surface area of this whole surface, what I'm going to do is it's going to be approximately adding up all the delta S's, which is going to be equal to adding up all of these cross products. All right, so, and another way to write this then is, this is going to be the double integral of the norm of RU cross RV times du dv. Sorry, I'm running out of space here. We're integrating over d. All right, so I'm going to rewrite that on another sheet of paper, and we'll see if we can get this down here. So what we have then is that S is going to be equal to the integral, the double integral over some region D. Remember, this is the domain in UV space. All right, and it's going to be our vector function defining the surface, partialed with U, cross product with our vector function that defines the surface, partialed by V, and we take the vector norm of that, and we then take our variables of integration are going to be du, dv. So let's talk about an example, and I'm going to talk about a very simple example of the half sphere. So we want to find the area. So we're going to find the area. So we already know what the area of a sphere is. So it turns out, a whole sphere has area of 4 pi. Okay. So of course the half sphere is going to be 2 pi. All right, so we already know the answer, what it's going to be, but we'd like to use this method on this simple example to give an idea of how it goes. This is their first time ever doing it. So let's talk about that. So what's going to be our R function? Well, first of all, what we have to think about is what's our domain. So one way to think about so a half sphere is going to be something like this, and it's going to look like that, and we can think of it as having, we can think of those as being the meridians, and these be the longitudinal axis there, and there it is. So what we're going to do then is we're going to take our D is going to be the circle underneath it. We're going to say that the radius, so this whole sphere is actually for the radius is equal to 1, and this is for the radius is equal to 1. I forgot to mention that. So we're going to talk about the ideal case of just a radius 1 sphere. So obviously if you try a different radius, you're not always going to get 4 pi out of it. All right, so radius is 1, and we're going to map it into x. So here we have our z-axis, and there's our x-axis, and there's our y-axis right there. Right, so there's the origin. So here's my d, and that's going to be my u and my v right there. And so we're going to take that circle, we're essentially going to bend the circle up and turn it into a sphere. So how do we do that? So let's define our R. It's going to be our vector function x, y, z. It's going to be equal to I, the ith vector. And so what is the x vector? Well, actually x is equal to u. We can think of that as just mapping straight on. And then y, of course, is going to be equal to v. And z is going to be equal to, well, what's the height? Given a particular point, on the xy plane, what's going to be the height of this sphere? Well, it's going to be, because our radius is 1, it's going to be square root of 1 minus x squared plus, x squared minus y squared. So that's what it's going to be. So we can write this down as IU plus JV plus square root of 1 minus x squared minus y squared times k. All right, so that's our vector function defining the surface. And then what we have to do then is do all this business here. So again, how do we break up? We need to create a bunch of patches for this space. So we could make rectangular patches, but that would be really onerous. So actually we're going to do another transformation to polar coordinates. So we're actually going to then say that if u and v, u is actually going to be lowercase r cosine theta, and v is going to be lowercase r non-vector r sine theta, just like before, and z is going to be equal to oh, sorry, no, there's no z here. What am I doing? There we go. And r, lowercase r, is going to be equal to u squared plus v squared. Okay. So with that coordinate transformation, we can rewrite this again. And what we're going to do here, what's the domain going to be in this case then? So I said u is going to be equal to r cosine theta. R is going to vary from 0 to 1. And theta here, theta is my new thing, it's going to vary from 0 to 2 pi, right? That creates, so we're going to go all the way out here, but we're also going to rotate all the way around. And that gets us all of the points inside that disk. So that's our domain D now. So we're going to not going to use this domain D. We're going to actually start with this rectangle. We're going to map that to a circle and then map that circle all the way to this half sphere. So with that in mind then, we're going to then go lowercase r cosine theta plus j times v is r sine theta plus, and then, okay, we see here, oh, I should have put, this should be u and v squared, not x and y squared. All right, so, but we see right there that that's going to be 1 minus r squared times k. Okay, looks good. So that's our function. We take this domain, which is going from 0 to 1 and 0 to 2 pi, and it's going to be a rectangle in polar space, in polar coordinates. And that maps to a half sphere in our Cartesian XYZ coordinates. So now let's do this thing. All right. So I'm going to give myself a lot of extra room here. So I'm going to rewrite this. R is going to be equal to I times lowercase r, or scalar r cosine theta plus j r sine theta plus k times 1 minus r squared. All right, so now remember the surface area was equal to double integral of d times the magnitude of the cross product ru and rv, the partials with respect to u and v. Or in this case now we're actually going to do it in terms of, it's the vector r partialed with the scalar r cross the vector r partialed with theta, we're taking the magnitude of that, times dr d theta. Okay, so that looks good. And our domain then is going to be, so we can rewrite that as, that's going to be 0 to 2 pi and 0 to 1. And then just put the same stuff in there. Let's put that there. All right, so we got to actually find, so what's r? R? Well, we just have to take the derivative. So that's going to be I. We'll take the derivative with respect to scalar r, and that becomes just cosine theta. plus j. Scalar r there, we take the derivative, and that becomes sine theta. And then we look at the derivative of this now. We see that, well, we just do a little chain rule on this, a little power law and chain rule, and we get negative k times r over 1 over 1 minus r squared. So there we go. All right, so now we need to take r theta. It's going to be I r sine theta, and we got to remember to put a negative sign there. And then it's going to be j r cosine theta. And then plus, so 0 times k, because there's nothing with theta over there. So when you take the derivative of it, you just get 0. Okay, so that looks good. So now we need to take a cross product. So the vector r partialed by the scalar r cross with r partialed by theta. So that's going to be the determinant of I, j. I'm going to give myself a little bit more runway here. Okay. And then we put our first row here. That's going to be at cosine theta. And then we have a sine theta. And then we have a negative r 1 minus r squared, all square rooted. Okay, so, and then the second row is negative r sine theta, r cosine theta, and then 0. Right. I, and that's going to be r 1 minus r squared, square rooted, times r squared cosine theta. That's all we get out of it. Minus j, and then j is going to give us a same thing as before, but we're going to get a positive. Yeah, we're going to get a positive out of that. So is that true? We're going to get a positive out of that? Yes, we are. Yes, we are. Okay, so that'll give us an r squared cosine. Sorry, because r squared sine theta all over 1 minus square root of 1 minus r squared. And then finally plus k, and we're going to get, well, we see that cosine multiplies by cosine squared times r, and then we have a minus sine squared, so that'll result in just r coming out of the thing. Alright, so that's the thing. And now what we need to do is take the magnitude of it. We take the magnitude, and that's going to be the square root of the squared components. Alright, so that becomes r to the 4th times cosine squared theta all over 1 minus r squared plus r to the 4th sine squared theta all over 1 minus r squared plus r squared. Alright, so we know that cosine squared plus sine squared is equal to 1. So we can collect all those terms, and we're left with an r squared plus r to the 4th over 1 minus r squared. Alright, so what do we do with this? Well, we can actually do quite a bit with it. So let's try, oh, did I, yeah, it looks good. This looks good. Okay, so so how do we simplify this further? This still looks a bit onerous. So it turns out This is straightforward enough. What we have to do then is multiply both sides by 1 minus r squared. We have to multiply to get like denominators. So we're going to go square root again. And we're going to multiply r squared by 1 minus r squared times r squared over 1 minus r squared. And of course that gets us a plus r to the 4th power. Okay, so let's simplify this down. Still have that square root there. We see r squared, r to the 4th, and there's a negative there, so those are going to cancel. And we're going to be left with r squared over 1 minus r squared. Okay, so that becomes r over square root of 1 minus r squared. Okay, that looks good. So now, of course, this is the part right here. That's what this is right here. So the next thing we need to do is actually compute the integral now that we've done all the big calculation. And it's going to be 0 to 2 pi, 0 to 1, r square root of 1 minus r squared, dr d theta. Now we can see right now that there's nothing with theta in here, so d theta can move right through the problem, and we can take that integral with just the d theta, and that becomes a 2 pi. And then we're left with 0 to 1 r square root of 1 minus r squared dr. Alright, so clearly this will lend itself to a U substitution, or actually we're going to call it a W substitution because we've already used our U variable. So W is going to be equal to 1 minus R squared. So dW dr is going to be equal to negative 2R, which is the same thing as dW over negative 2R is equal to dr. So we can put that all together here. That's going to be equal to 2 pi. And now we take the integral, but because we've done a change of variables, we put a 0 in there, we get a 1. We get if we put a 1 in there, we get a 0. Okay. And then we have an r square root of w. Everywhere we see a dr, we can put a dw over negative 2r in its place. 2's will cancel. There's a negative sign that goes out front, and these r's will cancel there. So we're going to get, and now we see we can move that negative sign, move it out front, but we see that we have a misordered limits of integration, and so what we can do is flip the sign and make it go from 0 to 1. We still have a pi sitting out there, and then we have a w to the negative 1/2 power, and that's going to be dw. That has a very nice antiderivative, which is the whole goal. So w to the 1/2 power over 1/2, and then we're going to evaluate that at 0 to 1, and that means that S, our surface area of a half sphere, is going to be 2 pi, just like we predicted. So there's a full example of a surface integral done from start to finish, where we had to both find our vector function here and compute the partials with respect to our input variables r and theta, compute all the cross products, which can take some time and some algebra, all the way down to actually producing the integral. So that's the answer. Thank you very much.